is very bright in radio actually. So this, so like I was saying, the 2 kiloparsec and the being visible in radio, visible in X-ray wavelengths, that's sounding more normal, like what happens sort of in our own galaxy as well, but it's a little bit bigger in scale. The radius of the central disk in M87 is 16 kiloparsecs. Oh, okay, I'm going home soon now. Okay, good. Congratulations on the hospital release. New flu virus. OMG. Congrats, Steven. Go home, take rest. Let me know later in the comments how you're feeling, and it would be nice to get an update. Thank you so much. Oh gosh, people getting the flu. So, putting those, speaking about those numbers again, the radius of the central disk in M87 is around 16 kiloparsecs, which you can compare again to our own distance from this from the galactic center. The sun and us, we're about 8 kiloparsecs away from the galactic center. So 16 kiloparsec long disk is not the most extraordinary thing. I mean, it is extraordinary, but it's still something relatable. We're seeing it at an inclination of 42 degrees. The observed spectrum of the disk reveals that it is rotating with a VC sin I of 460 kilometers per second, or a VC of 690 kilometers per second. So quite a bit of velocity there with the speed of the rotation. We can then calculate that the mass within 16 parsecs of the oh, wait a minute, I am reading this wrong. The radius of the central disk in M87 is 16 parsecs. I think I was reading it as kiloparsecs this whole time. Sorry about that. Wrong number there. I was reading this as 16 kiloparsecs and comparing it to our own distance of 8 kiloparsecs from the galactic center, but excuse me, M87's disk is 16 parsecs. That would make it kind of small. The radius of the central disk, let me read this again. The radius of the central disk in M87 is 16 parsecs, which is 4.9 times 10 to the 17 meters. We're seeing it at an inclination of 42 degrees. The observed spectrum of the disk reveals that it is rotating with VC sin I of 460 kilometers per second, or a VC of 690 kilometers per second. We can then calculate, like once you have your orbital speed, you can get what mass is within that radius. Remember, from Kepler's third law, we can then calculate the mass within 16 parsecs of the center as something like 2 times 10 to the 9 solar masses. Yes, that's Baji. Yes, you saw him. That's Baji over there. So the mass that's within the 16 parsecs of the center is 2 times 10 to the 9 solar masses. Oh wow. So there you go. That's the supermassive black hole at the center of M87, and it makes a lot of sense now, because the 16 parsec is of course very small compared to the kiloparsec that I was thinking it was. It wasn't. So within that 16 parsecs, we have this big mass of 2 times 10 to the 9 solar masses, which is the supermassive black hole at the center of M87. Sorry about the confusion. Hopefully I corrected all the numbers and you're good with it now. But now we have the supermassive black hole of M87 being 2 times 10 to the 9 solar masses, which comes from doing the math for utilizing the orbital speed, which we get from observed spectrum. Okay. Wow. Okay, great. M87